Hi, good morning, everyone. This is OHCOW COO Dave Wilkin. I'd like to welcome you to today's webinar on work-related heart disease. Our speakers today are Professor Sandra Dorman of Laurentian University and Andrew Zarnke, an occupational hygienist with OHCOW in Sudbury. We'll be holding questions until both presentations are complete. But we encourage you to put questions into the WebEx chat or the Facebook comments as we go along, so you get them out while they're fresh in your mind, and we have them racked up for the question period. This webinar will continue to be available via Facebook after it's complete, and will also be up on our YouTube channel within the next week or so. So we'll move on now to our first speaker. Dr. Sandra Dorman is a professor at the Faculty of Health at Laurentian University and director of the Center for Research in Occupational Safety and Health. She's done her doctorate in physiology and pharmacology, and her research program focuses on health prevention and disease prevention in the occupational setting. She's the author of more than 30 papers, and we're very pleased to have her with us here today to discuss work-related heart disease.
Good morning. Thanks for having me this morning. I'm excited to talk to you about this. It sounds a little creepy, but I really like pathophysiology as a topic. So today we're going to talk about heart disease, and the way the lineup I think will work here is that I'm just going to explain to you the basics of the most common types of cardiovascular disease. And then Andrew is going to talk about how it relates to risk in the workplace. So I will dive right in, and in general, to start a talk about disease, you want to throw out some numbers to try and get people's attention. And heart disease continues to be the number 2, and actually cancer and heart disease in Canada are number 1 and 2, and depending on the age group, sometimes, well, heart disease used to lead. I think cancer has just edged out heart disease more recently. And so not to go through all of this slide, but what I want you to get here is that I'm not talking about some stranger. I'm talking about probably you or someone you love developing, if not full-blown cardiovascular disease, then aspects of it, right? Or having risks for it. And just to highlight this little point here, 90% of Canadians have at least one risk factor for heart disease or stroke. And so I'm hoping that you'll take this presentation and personalize it in a way that induces behavior change. Because at the end of the day, that's how we manage chronic diseases, is we change what we're doing. So there was 2 other points I wanted to make around the numbers. The first was that heart disease is really in Canada a disease for almost all ages. If you look at these 4, circle graphs here, they're based by age. So age 1 to 24, 25 to 44, 45 to 65, 64, and then 65 and above. And the red triangle is the contribution to death. And you can see, with the exception of our youngest population, every age group has risk of heart disease. And the older you get, the more that risk increases. So again, highlighting behavior change and management, but at all stages in life, really, for prevention. And then I special note out to women, because I think women still often feel like cardiovascular disease is a man's disease, and it is not. As you can see here, 1 in 3 women's deaths are due to heart disease every year. And women, 9 in 10 women have 1 or more risk factors for developing heart disease. And again, if you look at the leading causes of death for women, 1 in 2 is heart disease and stroke. So cardiovascular disease is just as real a problem for women as it is for men. And I will, just because this is a bit of a tangent, but one of the reasons women die from heart disease is that sometimes people are uncomfortable performing CPR or, treating, or like in the public, if a woman passes out, people aren't comfortable with ripping open her shirt as potentially necessary for the treatment. And I'm telling you, any woman would gladly let you rip open her shirt if it saves her life. So don't hesitate because of that. Okay, so let's talk about cardiovascular disease then. And I've kind of broken it up into 3 sections, sort of starting with what's happening in the blood vessels, and then leading into what's happening in the heart, which, sometimes they call it coronary. Sometimes you'll see words like coronary artery disease. And then also what's happening in the brain. And the 3 are interrelated. So if we focus on, and the way they're interrelated is because you're either talking about blood vessels in the body, or blood vessels in the heart, or blood vessels in the brain. That's essentially the difference. So when we just introduced the topic about blood vessels, I put a picture over here that's showing you a cross section through a single blood vessel. And the first picture here is a normal, right? Or healthy, if you want to say, a blood vessel. And in a healthy state, you can see the diameter of the vessel is quite wide. I don't know if you can totally see it here, but the inside, the lining of the blood vessel is very smooth and slippery. And it actually tries to keep things from sticking to its edges. And it has a mechanism that allows that to happen, basically. Then 2 things can happen, and they can happen in either direction around atherosclerosis and high blood pressure. So atherosclerosis is the fancy word for hardening of the arteries, or sometimes people will say, a fatty plaque buildup. And that's what, if you look at this picture here, you can see this yellow buildup on the inside of the vessel. That is what a end stage or an advanced stage of atherosclerosis looks like. It's a fatty deposit on the vessel wall. Now, why do you get that fatty deposit? Well, in part, it can be due to high blood pressure. And it can be due to other things, things that basically tear the lining of this smooth vessel. And so that can do 2 things. One, if you tear it a little bit, it can damage and induce a little inflammatory effect right there. But in addition, that makes that shiny, slippery effect of the blood vessel go away. And so if you've lost that slippery effect, now things can kind of stick there, and you can get a point where you are more likely to develop a fatty plaque. Now, what causes that damage? Well, it can be, and Andrew may talk about some of the things in the workplace that can cause it, but often it's high blood pressure. And the reason for that is, and actually I'll maybe jump forward a slide and come back. So first and foremost, what is high blood pressure? So if we look to the left-hand slide here, normal blood pressure is where the vessel walls are somewhat relaxed and you have a large diameter in the middle of the vessel. And so blood can run through that vessel at a regular rate, if you want to say. High blood pressure is when you get a constriction of the vessel, where you're changing the diameter so that it becomes smaller. So think about your garden hose, right? Your garden hose, if you don't have any attachment on the end of the hose, the water's coming out of the hose and it's basically just falling out of the end of the hose, right? That's like a low pressure situation. Now put your thumb over the end of that hose and all of a sudden you've constricted the diameter of the hose, right? And now the same volume of water is going to shoot out at a much higher pressure, right? And you can spray your flowers, whatever you want to do. That's essentially what's happening with hypertension or high blood pressure in the vessels too. If you change the diameter, the rate that the pressure with which the blood goes through is higher. And if you look what's in the blood, sure, there are red cells and white cells that we think of them. But in a different context, you could call them projectiles, right? So imagine if your garden hose had little pieces of sand in it. In the low pressure situation, the sand just falls out onto the ground. In a high pressure situation, the sand shoots down and it could literally scratch your skin if you got in front of it, right? And so that's what's happening with high blood pressure, that can then cause these tiny tears in the artery wall. And the more tiny tears that you get, the more initiations of a single plaque that you can have. And then, you know, you can imagine your blood vessels are everywhere, but you can have more and more plaque developing throughout the body, the more tears you have, right? And so that's part of the reason why we want to control high blood pressure, is because controlling high blood pressure can control or reduce the development of atherosclerosis, okay? And then the thing with atherosclerosis is that it expands, and it expands in two ways. So we've talked about one. Basically, you know, you could have one plaque or you could have 20 plaques. That's one type of expansion, total number of plaques that you have. But you also could have a plaque, and again, I'll fast forward, I think, a bit. You could have a plaque that's only taking up part of the wall, or you could have a plaque that's extending all the way around the wall. And also, because a blood vessel isn't, you know, cross-section, it's long, it could extend down the length of a blood vessel too, right? So plaques get bigger as well as more numerous. And so if we go to this picture, you can see this is a fairly big plaque, and it has extended down the length of the vessel, but it's also extended all the way around the vessel. So we're now, the high blood pressure may be contributing to high pressure blood flow, but the plaque itself is also contributing to blood flow obstruction. So they feed off of each other. And in the worst case scenario, sometimes that vessel becomes completely occluded. And it can be occluded by a complete plaque, or because a clot forms in that narrowed vessel and blocks all the blood flow. So a couple of points here. So just a side view now of both blood flow and also how blood pressure is narrowing the diameter. This is just showing you from the length, and how the plaque can build up both around the vessel and down the length of the vessel. And similarly, in this picture here, you can see that what I'm trying to show you here is that if you block blood flow at a point in the vessel, right? So in this particular X-ray, they put a dye in the blood vessel to light it up. And right here where the red arrows are pointing, that's where the fatty plaque is. And you can clearly see not very much blood is getting through there, right? Which means the tissue that's downstream of that vessel is starved of oxygen. That's a key piece, because oxygen is one of the first things that will cause cell death if you don't have oxygen for a prolonged period of time. But it will also impact delivery of other stuff to the tissue, right? And so all of these pictures are just kind of highlighting that fact. The extent of the fatty plaque, the contribution to hypertension, as well as the fact that any tissue downstream of that is not going to get enough oxygen. So now let's overlay that knowledge onto the two main types of disease that cause death, which are coronary artery disease and stroke. So in coronary artery disease, you kind of have two main stages. You can have angina. I'm sure many of you have heard of that. And you can have myocardial infarction, which I changed here to MI because I was being tight with my words here. But this picture is just showing you cartoon-like the major vessels. So the heart's working super hard, right? It's beating. And so when it's circulating all that blood around, the first place that blood coming back from the lungs goes to is to the heart muscle. so that you can keep beating the heart, right? And so we've got blood directly coming off of the aorta that's full of oxygen that's going directly to the heart muscle to keep it happy and healthy and able to do all that work. And you can see these are the major blood vessels. Each of them are feeding all tissues around the heart itself, right? So in angina, what happens is you get a narrowing of one of the blood vessels that is, feeding the heart. And actually, if I go back to this picture, this is a great picture of angina in an X-ray. There is still blood flow happening to the heart muscle, but it's a lot less blood flow. And so that makes perfect sense when you think about the symptoms of angina, right? The person starts going up the stairs and working a little bit harder, and then all of a sudden, oh, it's, there's pain and shortness of breath and they have to stop. And that's because the muscle for the heart that's downstream from that angina is not getting enough oxygen, and so it's sending out distress signals, if you will. And so angina can become myocardial infarction, or myocardial infarction can happen in and of itself. And basically that is where a clot completely occludes the blood vessel to one of those blood vessels that are feeding the heart muscle. And this is a common one. And so you can see in this picture here, number one, that the clot has formed here. And number two is showing all the tissue in the heart that gets oxygen from that vessel, and it's not getting oxygen anymore. And if that clot isn't removed quickly, then those tissues die. And that's a heart attack, right? And so myocardial infarction is a fancy word for heart attack. The flip side is stroke. So stroke is the same thing essentially, except that it's happening in the brain instead of the heart. And, we typically can talk about two different types of stroke. I've got them on the right-hand side of the screen. If the clot occludes a vessel, then the same as the heart muscle, the brain tissue downstream of that vessel doesn't get oxygen and can die. But sometimes, because some of the vessels in the brain are so small and fine, that instead of blocking, it can burst, it blocks, but then the little vessel bursts, and then you get bleeding into the brain, which neurons don't like blood. And so that can damage or kill the parts of the brain. And often it's linked to actually the arteries that are feeding the brain. So the atherosclerosis is actually really predominant in these neck vessels, and a piece of the fatty plaque will break off as it expands and lodge in one of the smaller vessels into the brain. Just wanted to wrap up with a couple of extra points. So absolutely, pre-existing conditions worsen and accelerate atherosclerosis, high blood pressure. And that's why if you accelerate those two things, you increase your risk for heart disease and stroke, right? And so smoking is one of those things that accelerates the risk. And it does that because smoking drives, well, it can actually drive hypertension too, but it drives atherosclerosis. People who have diabetes will also at higher risk because of the dysmetabolism around fat metabolism, which can enhance fatty plaque formation. Obviously, people with high blood pressure are at high risk because it will drive atherosclerosis, and people that are overweight are also at higher risk, again, because of the driving of atherosclerosis. Having said that, there are also things that we can do to protect ourselves. And I know you know this, but hopefully re-inspire you. Big one is diet. Plants, people. Plants are miracle medication. If you can't change your diet to exclude things that are less healthy for you, just make a point of including more plants every day, and I guarantee your blood lipid levels will improve. So aim for 10 plants a day, and those are legumes, nuts, not just your classic fruit and veg, oats, go plant crazy. Certainly exercise is going to help. Management is key. If you have high blood pressure, managing your high blood pressure will prevent overdevelopment of atherosclerosis and can prevent heart disease and stroke. So don't ignore it. And then I leave you here with question mark, how does work potentially increase your risk? And I'll hand that off to Andrew. And if you have questions for me, you can certainly email me if you are too shy to speak of it in the meeting today.
Thank you, Professor Dorman. That was a great, very informative presentation. So again, we'll encourage people to put questions into the chat on WebEx or the comments on Facebook if you have any, and we'll bring those forward to the presenters after our next speaker, who is Andrew Zarnke. Andrew's an occupational hygienist at the Sudbury OHCOW Clinic. He's also currently the project manager for several of our occupational disease cluster projects, and he's working on completing a PhD in occupational health and safety at Laurentian University. His research right now is focused on better understanding how McIntyre powder exposure could have contributed to the development of cardiovascular disease. And he's going to present today on the question of tiny dust particles and cardiovascular disease. Andrew?
Thanks, Dave. Thanks, Sandra, as well, for the great intro to what I'm going to be talking to you about today. I'm going to be talking to you about occupational dust exposure and cardiovascular disease and how McIntyre powder kind of fits into that whole topic. So these are some well-known risk factors, and Sandra touched on some of these in her presentation. A lot of them are related to lifestyle choices like smoking, unhealthy diet, lack of physical activity, obesity, raised blood pressure, and so on. But what about environmental factors, and what about occupational factors? And one major one that I'm going to focus on today is PM 2.5, fine or ultrafine particulate matter, and dust in the workplace. First, I'm just going to touch on some definitions and talk a little bit about how our lungs deal with inhaled particles and how that can affect the cardiovascular system. The first two here, inhalable and respirable, are two that are used by occupational hygienists during dust sampling in the workplace. But the two I'm going to focus mostly on today are PM 2.5, or particulate matter less than 2.5 microns, or also known as fine particulates, and ultrafine particulates, or nanoparticles, which are particles that have a diameter of less than 100 nanometers. So that's 0.1 micrometers. So very, very small particles. And the image on the right shows you, kind of gives you an idea of the breakdown of the different parts of the lung. And the reason why the particle size is so important when we're looking at dust exposures is that the smaller the particle is, the deeper down in the lung it can get. And in the upper part of the respiratory tract, we have very efficient clearance mechanisms. The surface of the lung has hair-like structures and a mucous membrane that can very efficiently expel foreign objects like dust out of the lung, kind of like a conveyor belt system. Down in the alveoli, or the alveolus of the lung, where gas exchange occurs, it's a smooth surface, and there's no hairs and no mucus to really help get foreign particles out of the lung. So it completely relies on a very specialized immune cell called an alveolar macrophage. And it's this cell's job to engulf foreign particles, and through chemotaxis, or movement of the cell up into that conveyor system up higher, so that it can be expelled. It's also important to know, and you can tell by these little round images, or these little round balls that are the alveolus, there's a very large surface area for exchange to happen. That's where the gas exchange occurs. And that's also where the circulatory system comes into very close proximity to the interior area of the lung. So if we have reduced clearance because of dust exposure, you have these very small cells that can more easily cross that membrane and enter into the circulatory system where it can be translocated around the body and exert some of those effects that Sandra was talking about in terms of nicking and scarring, and really drive atherosclerosis in all different parts of the body. So in 2018, the World Health Organization reported estimates of 7 million premature deaths per year caused by just fine particulate exposure alone. The study in 2019 by Lelyville et al. That estimated that in 2015, there was 9 million deaths worldwide attributable to air pollution. And a lot of the research around this is focused on air pollution, but what they found over the years in studying this, that the part of air pollution that is the most important, that holds the strongest associations, is PM 2.5 levels. To put this into perspective in terms of smoking, one of the other lifestyle choice risk factors that everybody knows about, WHO actually estimates that the excess death rate from tobacco smoking at 7.2 million deaths per year. So you can tell right there that there's estimates now that fine particulates actually contribute to more mortality on a yearly basis than even smoking. That was a real eye-opener when I started studying this, and it really kind of flipped my idea of risk factors for cardiovascular disease on its head. So I'm going to talk about McIntyre powder. One, it's the main topic of what I'm researching, but it's also a great example of a PM 2.5 exposure, and I'll explain a little bit about why. So McIntyre powder is a very fine aluminum powder used in the mining industry to prevent silicosis. It was developed in response to the growing prevalence of pulmonary fibrosis caused by the inhalation of crystalline silica. So they thought that the chemical characteristics of aluminum would prevent the silica dust from staying in the lung, and it would allow your lungs to remove it or expel it more easily. And they thought that this would help people from developing silicosis. It was used in a majority of gold and uranium mines in Ontario from 1943 and 1979. It was used in other industries. It was also used across Canada. It was used very prevalently in mines in British Columbia. It was also used in many gold mines in Western Australia and other places around the world as well. But when we look at just Ontario, based on the mining master file record that we have, 27,500 mine workers in Ontario alone were exposed to McIntyre powder. So it was a large number of people that it affected. Here you can see an image of what a canister of McIntyre powder looks like. It holds 10 grams. And then on the right, you can see an image of McIntyre powder actually being expelled back in the 40s and 50s when they were using it. And you can tell just by the image that it looks almost like exhaust coming out of a diesel. I mean, it was very dirty, nasty stuff. The dose that was recommended was 1 gram per 1,000 cubic feet of locker room space. So they would expel the dust, the powder, into the locker room while the mine workers were getting ready to go to work, and they were told to breathe it in deeply to protect their lungs from silica when they were working underground. To give you an idea of how much McIntyre powder they would use at each treatment, this is actually a picture of the McIntyre mine in Timmins where it was developed. This locker room was 80,000 cubic feet. So based on that math, they would have to use 80 grams of McIntyre powder. So that means 8 of these canisters each morning before every shift went underground would have to be pumped into that space. So the workers would get the appropriate dose of McIntyre powder. What is McIntyre powder actually? So when we first started looking at McIntyre powder to research what the potential health effects might be, we first had to ask ourselves exactly what it was. So using actual samples of real McIntyre powder, we were able to do a detailed analysis of the physical and chemical characteristics of McIntyre powder. And although there was lots of interesting findings, the one that I'm going to focus on today is actually the particle size. So we were able to detect McIntyre powder particles from as low as 5 nanometers in size all the way up to about 5 micrometers. And I just want to note that there was a very small proportion of particles that were bigger than 1 micron. And there was a very large proportion of particles that were actually down below the 100 nanometer range, which puts it at a nanoparticulate. And what's really surprising when I looked at this image was that some of the smallest McIntyre powder particles are actually almost equivalent to the size of a single lipid molecule. And these lipid molecules are the molecules that make up the cell membrane of each one of our cells. So it really makes it clear how pervasive these particles can be in our body, not only in our circulatory system, but also, relatively easy to get into individual cells as well and have potentially intercellular effects. And then if we put that into context of our lungs, here's around where the alveolus is at, about a little over 100 micrometers in diameter. And then the alveolar macrophage, which is the sole structure responsible for removing particles out of the lung, at about just above 10 microns. So lung overload is an important process to understand when we're thinking about McIntyre powder exposure. Because McIntyre powder was such a high dose for a short period of time, you're basically inundating the lung with a very high volume of dust in a short period of time. So what happens in lung overload is alveolar macrophages become overwhelmed with particles. So lung clearance is greatly reduced or completely absent. And the smaller the particles can actually accelerate the process or speed up the process of lung overloading. And as I talked about before, fine and ultrafine particles are more easily translocated out of the lung and into the circulatory system. Through all of this investigation, we can pretty confidently say that McIntyre powder should be considered almost 100% PM 2.5 matter, and under the ACGIH definitions would be entirely respirable. Scientific evidence suggests that there is a dose-response relationship between PM 2.5 and cardiovascular disease, and I'll explain that in more detail in the next slide. Also, a very important point is that the small particle sizes and high dose rate of McIntyre powder favor conditions for lung overload. These conditions provide an opportunity for particles to translocate from the lung into the lymphatic system, the circulatory system, the heart, and other tissues in the body. Over the last 15 years, there's been a number of studies done on the potential effects of PM 2.5 exposure. And the relative risk for long-term exposures per 10 micrograms per meter cube increase in ambient 2.5 levels between 6% and 76%. I've just graphed this dose-response relationship, and using the most conservative estimate of 6%, you see on the x-axis, you see PM 2.5 levels increasing. On the y-axis, you see the relative risk from cardiovascular disease increasing. First blue dashed line on the left corner shows an average level of PM 2.5 in a city like Toronto. So it's about 13, 5 to 50 actually, it's a big range, but 13 is the average level of PM 2.5, and that's in micrograms per meter cubed, and that's a 24-hour time-weighted average. So that means the level of PM 2.5 goes up and down throughout the day, but they just average that out over the 24-hour period. You look at the next dashed line to the right. This is what an average peak exposure would be. So on like one of the worst days in Toronto, like a real smoggy day in Toronto, would be about 100 micrograms per meter cubed. You can see that the relative risk of that would correlate to about 1.6. So any relative risk above 1 is going to be an elevated risk. So this is about a 60% increase in your risk of developing cardiovascular disease, solely from your PM 2.5 exposure. Now, if we want to think about this in terms of McIntyre powder and where this would actually fit into this data, we would have to convert McIntyre powder exposure to a 24-hour time-weighted average. So here's just the basic calculation the number of so 35,000 micrograms divided by the number of minutes in a day, you get 243 micrograms per meter cubed. So you can see this red line shows exactly where it fits on this dose response relationship. And that would equate to almost 2.5 times your risk of developing cardiovascular disease simply from your McIntyre powder exposure alone. So these are just some points that I've kind of already described in the previous slide, but I wanted to have them here in writing. Any of these slides will be available after the presentation, so I wanted some of these details in the presentation. I also didn't want to leave out all the other exposures that have been linked to cardiovascular disease that miners specifically are exposed to. The miners that were exposed to McIntyre powder weren't just exposed to McIntyre powder. I mean, they went underground and worked every single day in the mining environment. So some of the exposures that have been linked to cardiovascular disease that are inherent to the mining environment are just ambient mine dust in itself, stress. So heat stress, thermal stressors have been shown to have significant effects on the cardiovascular system. In the mine, they were actually, like, depending on the type of mine and how deep it was and the ventilation that was there, mines can get up to 45, 50 degrees Celsius when you're working 12-hour shifts in that environment. So arsenic, which is inherent to gold mining, diesel engine exhaust, which has been linked to cardiovascular disease, nitrogenous byproducts from blasting, especially in a confined space like a mine. And also something that's come up with our work with another project is stress. So stress is an everyday risk factor for cardiovascular disease. And when you're working in a very dangerous work environment, your stress levels are going to be high. So it's just common sense that that is also going to be a major risk factor for cardiovascular disease in the workplace. And last, I also want to just talk about that there's obviously other workplaces where you can find these types of exposures that increase your risk to cardiovascular disease. So this is a picture of a worker transferring some molten metal in a foundry here in Sudbury called Nylon Castings. Nylon Castings was in operation from 1975 to 2007, and there was almost 2,000 people that worked there over that period of time. And we're working with some researchers and some past nylon casting workers to put together a full retrospective exposure profile for this workplace. And some of the things that we've identified right away as being risk factors for cardiovascular disease is the dust exposure. And then obviously the heat stress. These workers were exposed to some very significant heat stress. And then carbon monoxide was one of the main issues in this workplace as well, with some very, very high levels of carbon monoxide. And stress from a dangerous work environment. Some of the stories that I've heard firsthand from workers is astounding, that on a daily basis, you're having to step in to prevent significant incidents from happening. And just the knowledge of that potentially happening on a daily basis has to add significant stress to your everyday work environment. So that has to be a major risk factor for developing cardiovascular disease. My presentation, and I'd be happy to answer any questions. And thank you very much.
Okay, thank you, Andrew. We do have a question in the chat, and this is from Neil McMillan. Question regarding the WSIB policy on heart conditions. So document number 150310 in the operational policy manual has a qualifying condition: unusual physical exertion and/or acute emotional stress. WSIB routinely denies firefighter cardiac claims by stating that the firefighter did not participate in duties that were not expected of them, even though expected duties include wearing in excess of 50 pounds while carrying in excess of 100 pounds in high heat conditions, in an elevated carbon monoxide atmosphere, and while under the duress of having to accomplish tasks in a fast and effective manner. How can worker representatives convince WSIB that although expected, these are still unusually physical and stressful conditions?
That's a really great question. And I can comment on some of that, and maybe I'll get Dave to potentially comment as well on some of the legal aspects of that. But when we're talking about compensation, especially with cardiovascular disease, it's difficult for all the reasons that we've just learned today. There's a complex array of risk factors, many of which are lifestyle risk factors. And the science behind the occupational factors, there's lots out there, but it's also lacking behind some of the other risk factors that are out there that get focused on. So when we're talking about compensation, the type of, you really have to put it into context, and especially when we're talking about chronic exposures, long-term health effects, it makes it even more difficult. So I don't know, Dave, if there's some.
Well, can I jump in as well?
Oh, absolutely.
One of the things I assume you're talking about structural firefighters here, not wildland firefighters, correct? So two things that can be done or that are documented. First and foremost is there's a lot of literature out of the United States that shows firefighters having cardiac events within hours or days after a fire event, right? And that's very similar to the data that Andrew's referring to around pollution-related deaths, right? You can readily track bad smog days and increased risks in or increased occurrences of both cardiovascular deaths as well as increased hospitalizations and medication use. And so to some degree, tracking of events, I think, could be better done in Canada, but also referencing that body of literature, I think is somewhat powerful. The other thing I would note too, I think particularly with the structural firefighters, is the diesel particulate buildup that's in many of the fire stations themselves. Not all of the fire stations yet have been able to install the infrastructure to redirect the diesel that's coming off of the truck, when it's on and it's in the fire station. That should be a priority issue, but in the same way that you could track estimated lifetime exposure to diesel particulate and potentially other particulate, I think you could make estimations for firefighters too, which I think would strengthen a WSIB claim in the same way that they make estimations for lifetime exposures for industry occupations.
Yeah, and I would just jump in quickly from a legal point of view. Any WSIB policy that attempts to deal with a condition like this on an exclusionary basis, so to say, here are some conditions that must be met, and if they are not, entitlement will be denied, certainly can't be sustained beyond the merits and justice point. As Andrew and Sandra both mentioned, there's a lot of specific information out there about how the factors that firefighters are encountering on a regular basis increase the risk of heart disease. I just had a question about the policy also includes a specific reference to inhalation of smoke and various noxious gases and fumes, for example, firefighters. I'm wondering, do they actually make a distinction between a situation where there's some documented overexposure to smoke on a particular day and then a heart attack shortly thereafter, and then simply deny the rest based on that did not happen, even though the worker was carrying a ton of equipment in heat under stress and all that sort of thing. But certainly looks like there's a lot of room to work towards the tribunal level, at least, on putting together the the evidence for causation, even within generally expected conditions for a firefighter. Okay, there's another question in the chat. Is anyone in Canada tracking and publishing cardiovascular health risk or associated death risk data in occupation similar to CAREX or the OCRC burden of occupational cancer does?
Well, part of my PhD work is actually going to be collaborating with the Occupational Cancer Research Center. They published a study looking at neurological effects in 2019. And that data set that they have used the mining master file to gather information on McIntyre exposure and then linked that to OHIP records. That allows us to gather medical follow-up information for mine workers that were exposed to McIntyre powder. So we're working with them to potentially do a detailed analysis of that data set with respect to miners' risk to cardiovascular disease. So that should be really interesting.
Sandra, anything to add on that?
Sorry, what was the very first part of the question?
So it's whether there's anyone in Canada tracking the cardiovascular health risk associated with different occupations in the same way that CAREX or OCRC does for cancers.
Yeah, I'm not aware of it. I mean, the biggest research I think that is done that's tracking it is all around the epidemiology of air pollution in relation to it, because that data is readily available. I think that people are not, because it's a chronic disease, but also and so it has multiple causes, but also I don't think there's been a lot of industry desire, I guess, to track that either. So no.
I just had a little side question. I'm not sure if either of you will have this information at your fingertips, but it seems to me that when I was looking at some data on workers' compensation claims for occupational disease in Germany, that they had quite a high number of heart and cardiovascular disease claims that were accepted, certainly relative to us and relative to cancer claims. Do either of you have any knowledge of what's going on in other jurisdictions with respect to that sort of question?
I don't have any data offhand to help answer that, but I do know just from listening to Dr. Paul Demir's presentation that in Germany they have a much larger list of presumptions for compensation. So that would probably be the first place I would look to see if there is some specific presumptions for cardiovascular diseases. That would be where I might start to that.
I would echo, I'm not aware. I think cancer has been a big focus in tracking occurrence, and also types has been a much larger focus than cardiovascular per se. But I would have said maybe Australia. I think Australia's been pretty terrific in leading some of these initiatives, but I'm not aware of any.
Okay, thanks. So I don't see any questions although I might not have a good view here on my iPad over on the side. I don't see any questions in the Facebook comments, and I don't see any more in the chat section. I would encourage everybody to please go to the link in the chat for the survey about today's webinar, which helps us obviously to keep improving the content that we're offering to folks. And if anybody else does have some questions, please feel free to unmute yourself, turn on your camera and wave your arms or whatever, because this is the last call. We still have about 5 or 6 more minutes.
It's Kimberly. I just wanted to ask the audience, so we're running this winter OHCOW series, and if you do, when you fill out the evaluation, it'd be great to have content ideas. we are noticing extreme attendance at our, our occupational health or ergonomics type webinars, and another set of really great attendance at our COVID related webinars. So if you have ideas, this one is pretty low in attendance, but very important to us to get the messaging across. So please, a couple of things, please do suggest content. Give us an idea of, utilize the video when it's completed to share with your network, because we can count, distribution that way as well, and give us feedback. So it just was really curious to reach in terms of idea content, and encourage sharing at joint health and safety committees, or, this information after it's been provided to you.
Thanks, Kimberly. And yes, as I pointed out at the beginning, on Facebook, the entire webinar will be available immediately if you go to OHCOW's, if you direct someone to OHCOW's Facebook page. They just need to click on the presentation there, and it will run from the beginning, starting right now, and on an ongoing basis. And then in that edited version will be posted to our YouTube channel within the next week or so, and we'll be sending out a notice when that happens. Please make sure that your contacts who might be interested in this presentation are referred so that they can watch it as well. And if you have specific questions related to cases, like Neil's, and we're gonna talk to him some more about that whole issue from OHCOW. If you have specific cases, WSIB claims, or issues arising in your workplace or in your profession, please contact your local OHCOW clinic, and we'll do what we can to help you out. Okay, last call for questions. Seeing none, we've finished just about right on time today. Thanks everybody for your attention, and thanks so much to Professor Sandra Dorman and Andrew Zarnke for great presentations today.